Good morning, students. This lesson is of class 9th for the subject of physics, topic propagation of sound in a medium, which is covered in chapter 8, propagation of sound waves, given on page number 175 of your textbook titled Concise Physics by Selena Publications. This lesson is submitted to you on 12th April 2021. Students, last week we have learned about transverse wave. Today we will study sound wave, which is an example of longitudinal waves. First of all, let us learn what are sound waves. Children, when a source of sound vibrates, it creates a periodic disturbance in the medium. The word periodic means regular, regular after fixed interval of time. So when a source of sound vibrates, it creates a periodic disturbance in the medium, and this disturbance causes a wave which travel through the medium. This is a sound wave. Sound wave travels in form of compressions and rarefactions. Children, we will learn these terms today in the further lecture. Now coming to longitudinal waves. Longitudinal wave is a wave in which the particles of medium vibrate about their mean positions in the direction of propagation of sound. Children, in longitudinal waves, the particles move in the same direction as the direction of wave. These waves can be produced in solids, liquids, as well as gases. And such waves always require a medium to propagate. Children's sound travel in air in form of longitudinal wave. So let us understand the meaning of longitudinal wave further. So students, see longitudinal waves. Now when you compress it, the medium particle moves along the direction of wave propagation. Here what is happening? Children, the particles are moving along horizontal direction, and the wave is also propagating along horizontal direction. So that means the wave and the particles are moving along the same direction. The wave's direction is horizontal, while the particle medium or the medium's particle is also moving in the same direction. Children, we did transverse wave last week, in which the particles of the medium were vibrating perpendicular to the direction of wave propagation. For example, if the wave is moving along horizontal direction, the particles were vibrating along vertical direction. So these were transverse wave. The direction of wave and motion of vibration of the particle were perpendicular to each other. And today we were learning about longitudinal waves where the particles are vibrating along the direction of propagation of wave. So, sound is an example of longitudinal wave as it requires medium to travel. Now further today we will learn two new terms under the category of longitudinal wave. First term is compression. It is the region in medium where the density and pressure in the medium is maximum. So it is the region in the medium where the density and pressure in the medium is maximum. And rarefaction is this region where the density and pressure in the medium is minimum. So children, in the below given figure, number 1, you can see the formation of compressions and rarefactions. Compressions are the region of high density and high pressure, while in rarefaction, the vibration of particles is farther from each other, and this is a position, this is the region where the medium particle is having less pressure and less density. Thus, children's sound waves are also known as pressure waves, since they are moving via change in pressure along different regions. So children, sound propagates in the medium in form of compressions and rarefactions, and if we are having a speaker, this is the way a sound moves. So children, you can see a region where the particles of the medium are close to each other. These regions in the direction of wave propagation are known as compressions, while there are certain regions where the particle medium are at a greater distance with respect to each other, and these regions are known as rarefactions. In sound waves, the wave will travel in combination of compression and rarefaction. Again compression, rarefaction, compression, rarefactions. In this manner, as you can see here in this video, compressions and rarefactions are the region of high pressure and low pressure respectively. Compression is a region of high pressure and high density. Rarefaction is a region of low pressure and low density. So children, what is the direction of the particles here? The particles here will be vibrating along the direction of motion. So here, what is happening? So let us see sound waves and longitudinal wave. The particles are moving along the direction of wave propagation. The particles are also moving horizontally and the wave is also propagating in a horizontal direction. So, sound waves are longitudinal waves and they are also known as pressure waves. So, children, if we throw a piece of stone in the still water, a sound is heard and ripples in concentric circles can be seen going radially outward. If you throw a stone in a still water, what happens? You see circular waves formed, and those circular waves, in these waves you form ripples, and these ripples are in form of concentric circles. The word concentric means circles having the same center. So, if we place a cork on these waves, we will observe that cork will move up and down, but it does not move ahead. If you are having a cork placed in on the ripples, the cork will move up, down, but it will not move to the other place. This shows that vibrating particles of medium transfers energy stored in them in forward direction, but the particle in itself remains at same point. So the medium particle will transfer their energy to the next level of medium particle and then they will come back to their original state as we have done earlier in the lecture provided to you on 5th April 2021. You can see figure number 3. The particle is moving up and down at the same point, but it is not going in the forward direction. So children, for longitudinal wave, now wavelength is defined as distance between two consecutive compressions or distance between two consecutive rarefactions. Earlier last week, we defined wavelength as distance between two consecutive crests. Why? Because transverse wave used to travel in form of crests and trough. Transverse wave travel in form of crest and troughs. So the distance between two consecutive crests or two consecutive troughs was known as wavelength in case of transverse wave. Children, here longitudinal wave does not travel in form of crest and trough. Rather, it travels in terms of compressions and rarefactions. Thus, the distance between two consecutive compressions or two consecutive rarefactions is known as longitudinal waves. Children, let us learn about wave velocity and wave motion. Wave velocity is defined as distance traveled by a wave in 1 second. It is constant for a given medium and depends on density and elasticity of the medium. So on what factors wave velocity depends? Wave velocity depends on the density and elasticity of the vibrating medium. Children, since it is the velocity of wave, thus its SI unit will be meter per second and its CGS unit will be centimeter per second. Now coming to wave motion. Children, wave motion can be defined as speed with which energy is transferred from one place to other place. Children, wave velocity was the distance traveled by the wave. How much distance a wave is traveling in 1 second. While wave motion is the speed with which the energy is transferred from one place to another. It is not the velocity of individual particle of the vibrating medium. Now children, today we will learn about relation between wavelength, wave velocity and frequency. The symbol of frequency will be taken as nu. Nu. Name of the symbol is nu. 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 And what does it represent? It represents frequency of the vibrating particle. So children, as we know that wavelength is the distance traveled by wave in one time period. And you also know the formula that distance is equal to speed multiplied by time. So how to write down distance? Distance can be written as wavelength. Speed is to be represented by letter V, while time period can be written as capital T. Time period means capital T. So from here we can find velocity, which can be written as wavelength upon time period. So children, what we are doing here, I am saying that distance is equal to speed into time period. Thus, what is speed? Wavelength upon time period. So can I say that wavelength multiplied by 1 by time period is velocity? Just note this step. What I have done, I have written wavelength as it is and the denominator is written as multiply by 1 upon time. If you solve this lambda into 1 upon t, now lambda multiplied by 1 is lambda only. So lambda upon t can be written as lambda multiplied by 1 upon t. Why we have done so? Because students, we know that reciprocal of time period is known as frequency. What is frequency? It is reciprocal of time period. So the relation can be written as now V means velocity, is equal to wavelength multiplied by frequency. So we will be having a formula that V is equal to nu frequency multiplied by wavelength. So V is equal to nu lambda. Children, learn this formula as it will be used in numericals also. V is equal to nu multiplied by lambda. Now children, note that speed of sound in different medium is always different. For example, speed of sound in air is 330 meters per second, and speed travels fastest in solids, but they cannot travel through vacuum. Now let us do few numericals. Children, see numerical number 1. Ocean waves of time period 20 seconds. What is the time period? 20 seconds. Have wave velocity 25 meters per second. So let us find the wavelength and the horizontal distance between a wave crest and its adjoining wave trough. So children, first of all, the wavelength will be velocity multiplied by time period. So that is 20 multiplied by 25, which comes out to be 500 meter. Now children, distance between two consecutive crests is known as wavelength. But they are asking for the distance between crest and the adjoining trough. So this is half of the wavelength. Distance between first and second crest is wavelength. So distance between the starting point of crest and starting point of trough will be half of wavelength. So 500 divided by 2 will be 250 meters. Coming to the second question. A source of wave produces 50 crests and 50 troughs in 0.4 seconds. You have to find the frequency of wave. Children, such a question is in your back exercise also, and it is a very important question. Now a source is producing 50 crests and 50 troughs. Children, one crest and one trough forms one wave having a wavelength lambda. So one crest and one trough forms one wave. That means 50 crests and 50 troughs will form 50 vibrations, 50 waves. Okay? So 50 vibrations are produced in a time of 0.4 seconds. We have to find frequency. So children, how to do this question? This question is based on the definition of frequency. Now frequency is defined as number of vibrations made in 1 second. Number of vibrations produced in a time period of 1 second. In this question, in 0.4 seconds, we are having 50 vibrations. So that means in 1 second, we'll be having a vibrations of 50 divided by zero point 0.4. 50 divided by zero point 0.4 vibrations. So that will be your frequency in hertz. So students, with this, I come to an end of this interactive session, and you all are required to do numerical number 1, 2, 3, 4, 5, 6, 7 and 8 in your physics notebook. All these numericals are given on page number 183 of your physics textbook. Thank you, students, and have a nice day.